Hello. At this lecture, we're going to review the general balance equation. So the reason that we're going to look at the general balance equation in this lecture is because balances basically are the basis for chemical reaction engineering and chemical reactor design. Essentially, we spend a lot of the semester deriving and solving mole balances and energy balances. So if we have a reactor and we couple together the mole balance and the energy balance, we can call that the set of design equations for the reactor. And we can use that to learn how to design a reactor. For example, how much volume is required, or how much catalyst weight is required, or how much coolant is needed, or how much heat must be input in order for the reactor to carry out a reaction at an appreciable rate, maybe to achieve some selectivity, and certainly to stay within a temperature range that's safe. So all of this comes from balances. So in the first part of the class, we're going to look at mole balances. In the second part of the class, we're going to add in energy balances as well. So to motivate all of this, let's recall what the balance equation is. What's the general form of the balance equation that we think about as chemical engineers? So the accumulation is equal to the flow in minus the flow out plus generation minus consumption. So that's the general form. Now there's some special cases. So there are two such cases are when we deal with mass and energy. So there's something about mass and energy. They can't be created or destroyed. What that means is they can't be generated or consumed. So when we look at mass and energy, so mass, and when I say mass, I mean mass, like kilograms, pounds. When we deal with mass and energy, the balance equation turns into this: accumulation is equal to the flow in minus the flow out. Now, when we're dealing with moles, we can have accumulation and consumption terms. So think about a chemical reaction. Pick your favorite reaction. Many reactions have different numbers of moles on the reactant and product side. So one example is carbon monoxide oxidation. 2 moles of carbon monoxide gas reacting with 1 mole of molecular oxygen gas reacting to form 2 moles of carbon dioxide gas. So on the reactant side of that reaction, there are 3 moles. On the product side, there are 2 moles. So you have 1 mole is being net consumed over the course of the reaction. Now, if we were to do a mass balance on that reaction, we would find no generation or consumption, but the moles can be generated or consumed. So when we're dealing with moles, then the generation and consumption terms are valid. Another case that we can think about or look at is the steady state system. So what happens at steady state? Steady state, the accumulation term goes to 0. And another special case that we're used to looking at as chemical engineers is the batch system. So how do I manipulate the balance equation for a batch system? So in this case, the in and out terms go to 0. The in and out terms are equal to 0. So talking about chemical reaction engineering, we're often writing our material balances, in fact, all of our balances, over a system volume. So we have a reactor. Within that reactor, there's some fluid. There's a reaction going on in the fluid, and the balance is being written over that system volume. So we're often writing the balance over a volume. And we're usually writing the balance for some chemical species. So writing for a chemical species. If we go back to the carbon monoxide oxidation reaction, for example, we might write a balance over carbon monoxide. So for example, EG, for example, we might write it on carbon monoxide gas. a lot of times in this class, we don't actually talk about actual compounds. We use symbolic compounds. For example, we'll look at a lot of reactions in the form A plus B goes to C. So in this case, we might say our chemical species is species A. In fact, a lot of the balances that we write in this class are going to be on species A. So let's draw out what this looks like. So I'm going to draw a volume and we're going to write a balance over it. We're going to think about how the balance would, or how the terms in the balance equation play into the thing I draw. So I don't want to draw anything that's known. I'm just going to kind of draw some shape, any arbitrary shape. So, and this is a two-dimensional shape, but let's pretend it's three-dimensional. So I have some three-dimensional blob here. So thinking about the balance equation, I know that I can have flow in or out. So I can have flow in and I can have flow out. So here we have material flowing in and out of the system, material crossing the system boundary. So this line here defines the system. Anything within there is the system itself. I have flow coming across the system boundary, flowing in and out. Happening inside, I can have my accumulation if I'm not at steady state. And this is also where I can have my generation and my consumption. So those things are happening within the system boundaries. In chemical reaction engineering, for the sake of simplicity, we tend to group the generation and consumption terms. So they get grouped into one term, which is called net generation. So in CRE, the generation and consumption terms are lumped into one, and in fact, let's say one net generation term. That's still bad. And we're going to call this term G, net generation. And since we're writing this for a species, we're going to call it G sub J, for species J. And actually, we're going to get rid of this term pretty quickly in the next lecture, so don't get attached. So thinking about species J, if species J, I have some reactions going on, I have multiple reactions going on, and if I take all those reactions and add them all up, I find that species J is being net consumed. In that case, then GJ should be what? So GJ should be negative. So the reason for this is proper accounting. So we want the generation consumption term. If something is being net generated, then as in the mole balance, then the net generation term should be increasing its quantity or its amount. If something is net consumed, then the net generation term should be decreasing its amount in the balance. So if it's decreasing the amount, then this term should be negative. And in contrast, if species J is net generated, then GJ should be positive. So this is a key point. This is an accounting issue. So when we're doing balances are really just accounting. How much of something do I have? What's happening? And how is that changing the amount of something that I have? To ensure that we have proper accounting, we need to make sure that our terms are entering in with the right sign, either positive or negative. This is simple when we're thinking about this GJ term. I have an amount, and I'm either net generating or consuming. It will get more difficult when we replace that GJ with a reaction term, and it's particularly when we get into cases of multiple reactions. But the key point is when you go to do your balance, always be cognizant of whether your species is being generated or consumed, and then use logic to make sure that it's entering in the balance equation in the way that correlates to what's going on in your system.